Hi, I'm Ryan Baker, and this is Big Data Education. Today we're going to wrap up our week on relationship mining with a discussion of network analysis. Network analysis is an analysis of anything that can be seen as connections between nodes. The most common case, and the one you'll usually see, is social networks. For example, connection between friends on the internet, connections between students in a class. I know some of you are forging connections, not just in our forums, but also on Twitter, on Facebook, and other places. And connections between collaborators in a work project, including group teamwork. Regardless of what your domain is, there are a few general postulates of network analysis. There are these things, which are referred to as nodes or vertices. And these things, these nodes, have connections to other nodes. And these connections can be referred to as ties or links. So for example, we got people, those would be the nodes, and we have email conversations, that would be the links. Nodes can have different types of identities. Maybe we have instructors, students, TAs, and links can have different types of identities. Maybe we have helpful posts, and insult posts, and off-topic posts. And links can have different strengths. Maybe we have best buddies and kind of bare acquaintances. Here's an example, and it's actually student work groups from Judy Kay and Kalini Yossef's group in Australia. Here we have two different groups of students who are working on the same assignment. And you can see that one group, everyone's talking to everybody, and the other group, 3 students just did everything by themselves. And each of the students is a node. Each of the links between students is a tie. This might be, in this case, students working on the same resource. And you can see that there are weaker ties and stronger ties. The cyan to green students in your graph to the left have a pretty weak tie, whereas the blue to pink students at the top of that graph have a very strong tie. And of course, the pink to red student on the other graph have no tie at all. So which student group works together better? Well, I said one does, and you can kind of tell which one is working together. Which is the most collaborative pair of students? Well, it's a little hard to tell, but probably it's actually this blue to green one on the sparser graph. Who's the most collaborative student? That's also a little hard to tell. But probably in this case, it's the pink one. The pink one talks to everybody in his or her group and has relatively strong ties with everybody except for yellow. Now, in a graph of classroom interactions, there could be several different types of nodes. There could be teacher nodes, teaching assistant nodes, student nodes, project leader nodes, project scribe nodes. Similarly, in a graph of classroom interactions, there could be several types of links. There could be leadership roles, maybe X leads Y. There could be working together on some learning resource. There could be a helping act. There could be a criticism act. There could even be an insult act. And you note that the links could be directed or undirected. Working on the same learning resource together kind of seems undirected, but an insult is probably inherently directed, at least at first. Also, in a graph of classroom interactions, links could be stronger or weaker due to 2 things. The intensity of the act, is the student just saying, I don't think you did very well, or are they saying, you're a loser? And the frequency of the act. Does a student insult another student once, or do they do it every single day, which might even get into bullying? We can use network graphs and network analysis to study the patterns and regularities of the relationships between the nodes. One such example is density, which is the proportion of possible lines that are actually present in the graph. So what's the density of these graphs? The one on the left, every single possible connection occurs, and so it's 100%. The one on the right could potentially have up to 15 connections, but only has 3, which is 20%. Density could be used to figure out how collaborative a class is overall. It's no question that the graph where everyone's talking to everybody is probably a more collaborative class than the ones where no one's talking to anybody except 3 kids. A node is reachable if a path goes from any other node to it. So for example, which nodes are unreachable here? It's the pink, red, and yellow on the right graph. And you can think of this as meaning, are there any students who don't collaborate with anybody at all? Geodesic distance. Geodesic distance is the number of edges between one node and another node M in the shortest path connecting them. If we look at a student social network, and this is work by Shane Dawson, looking at an online class, we can see that the geodesic distance between these 2 points is 4, because they have 1, 2, 3, 4 steps to get between them. Between these ones, try to do it yourself really quickly, pause the video. The answer is 7. 1, 2, 3, 4, 5, 6, 7 links. How about these 2? Well, in this case, there's no way between them, so it's actually infinite. One way you might use geodesic distance is to say, how many people does an idea need to go through to get between people? Another construct we might want to think about is flow. how many potential paths are there between node N and node M that don't repeat a node? So what's the flow here? Well, here's one path, here's another path, here's a third path. So there were 3 possible paths between these 2 nodes. So flow might represent how many possible paths are there for an idea to go between people. Centrality. How important is a node within the graph? Which kids are the popular or influential kids? The kids who you want to persuade that math is cool and crack is whack. Well, there are 4 common measures of centrality: degree centrality, closeness centrality, betweenness centrality, and eigenvector centrality. The first one is nodal degree, which is the number of lines that connect to a node. So all the nodes on the left graph have nodal degree of 5. And on the right graph, the blue, cyan, and green have nodal degree of 2, whereas the pink, red, and orange, yellow, have nodal degree of 0. In this example, Dawson's example, this very central node is actually the one with the most connections. It's got 1, 2, 3, 4, 5, 6, 7, 8. With nodal degree, you can also think, if you've got a directed graph, a graph with arrows, about in degree, the number of lines that come into a node, and out degree, the number of lines that come out of a node. So if you think about that in school terms, think about the student who everyone talks to and the student who talks to everyone. Might not quite be the same thing. A second measure of centrality is closeness. A node's closeness is defined as the sum of its distance to other nodes. The most central node in terms of closeness is the node with the lowest value, the node with the lowest average distance to everything else. Now you might note that strength can be used as a distance measure for calculating closeness. In other words, if you have strength on your links, you could actually use this information and say that higher strength is closer nodes. A third type of centrality is betweenness centrality. The betweenness centrality for a node N is computed as the percent of cases where for each pair of nodes M and P, for any other pair of nodes, does the shortest path from M to P pass through N. The percent of cases where the best way to get from M to P goes through N is the betweenness centrality of N. So for example, what's this node's betweenness? For this graph, the betweenness is high because each group can only get to other groups for this point. There's actually 5 groups that each independently can only get to the other groups through going through I. So it's going to have pretty high betweenness. How about this node's betweenness? It's going to be low because there's actually only one point that connects to anything else through it. What about this node? It's going to have no betweenness. Nothing goes through it. This is the least popular kid in the whole graph. Betweenness 0. A fourth type of centrality is reciprocity. What percentage of ties are bidirectional? And this can be computed as the number of bidirectional ties over the total number of connected pairs. And finally, there's eigenvector centrality, which has complex math, which assigns centrality to nodes through a recursive process where more and stronger connections are positive, and connections to nodes with higher eigenvector centrality contribute more than connections to nodes with lower eigenvector centrality. So you assign each data point centrality based on its connections, and then you look at who each point connects to, and you keep repeating and iterating on this until you converge. This is actually a key part of the original PageRank in Google. So it's actually a pretty cool algorithm that has some major real-world impacts. So network analysis. There are lots of uses for network analysis. Lots of methods, lots of uses. It's particularly useful for studying collaboration. Group-based learning, collaboration among teachers, networks of influence. One question of particular interest to me is, why do some educational interventions seem to be dominant in specific regions? Why is assessments based in the Northeast and Reasoning Mind is based in Texas? Another use of network analysis is in epistemic networks, which relates skills, knowledge, identities, values, and epistemological elements in specific students. They're used to determine whether a student's pattern of performance and knowledge demonstrates characteristics of expertise by comparing the graph of a novice student to an expert student. And to learn more, see the link here. Next week, we're going to move on from our discussion of network analysis, and you can actually see that even though today was on mathematical analysis of networks, I did a lot of visualization. Next week, we're going to segue from here into looking at other visualizations, learning curves, learnograms, moment-by-moment learning graphs. So I look forward to seeing you next week. I'm Ryan Baker. This is Big Data Education. Thank you very much.